Thank you, Mr. Chairman. I have to also to express my regards to Dr. Olga and to Professor Grigori Nikiforchin. I know that he couldn't make it. So today I will present a collaborative work between the University of the Aegean, Hirion Helmholtz Centrum at Gestacht, and National Technical University of Athens. The work is actually of my PhD student, Christina Margarita Charalampidou. Oh, it's working? Okay. But she couldn't make it, so I'm presenting her work dealing with corrosion on aluminum lithium alloys. It's some preliminary studies. It's a new project that has started, a Greek national project, 6 months old, and we are simply reporting the first results of our work. So the agenda will be like this. I will first motivate, but for those of you that you are not aware of the aluminum lithium alloy, lithium is an old story to aeronautical aluminum alloys. We want lithium because it's light density, and therefore the structure can be lightweight. So it's an old story starting from the past, even Russian alloys in the 50s and 60s, but at the latest decade we have third generation aluminum copper alloys with increased mechanical properties. Their microstructure is really a pain, meaning it's a complex microstructure consisting out of different phases, so it's very, very hard to manipulate as strengthening precipitates. Nevertheless, they play a critical role on not only the mechanical behavior, but also in the corrosion mechanisms. So this is something that we plan to investigate in the 3 years project that we are running at the moment. So, and this is the last slide of my introduction. Where is this being used? Nowadays, it is being used mainly at the fuselage of Airbus and Boeing. Okay, mainly at the barrel of the structure. So, and now I will shift to the corrosion problem. Why it is necessary to study corrosion problem? Because it's mainly one of the major important factors for problems of damage. And how to simulate corrosion? You see, there are many. There is one standard. It's the standard ASTM G34, but this is dealing also only in 2000 series aluminum alloys. Nothing special with the aluminum lithium alloys. So the purpose actually of this work is to investigate which is the most appropriate corrosion solution, to investigate the corrosion mechanisms that should be involved on these new alloys. So to this end, we have tested 3 different solutions. The classical one, according to G34, that is highly susceptible to exfoliation. Exfoliation means that cracking and exfoliation takes place after some corrosion exposure times. The typical one with sodium chloride. And we investigate another one that is most promising, the Harrison one, that could be found also mainly to magnesium, but we have evidence that might be most appropriate for identifying the corrosion mechanisms. So this is the flow diagram. Of course, we machined the tensile specimens, surface cleaned, corroded the specimen, and then performed the tensile test and had an evaluation. So before the mechanical test, we also had some impedance tests, electrochemical tests, just to have an idea of the corrosion susceptibility. I do know, okay, and then we perform the test. This is OCP, open circuit potentiostat, typical for electrochemical evaluation. And then the tests were performed at a tensile tester. So I have to report briefly and very quickly. These are the electrochemistry tests for the sodium chloride solution. I don't report the results on the EXCO because the EXCO, as you can see, is very, very quick. After 2 hours, you have, it's just like having a bomb with the corrosion and the corrosion mechanisms. So we cannot study them with electrochemical tests. So that's why I will simply report the Nyquist plots for sodium chloride and the Harrison. What do we need this Nyquist plot? As you can see, all these are capacitive loops, and we have an identification that something happens. For example, yes, we have a corrosion mechanism ongoing. The first one is that the protective layer, the passive layer, breaks, and then we have a degradation on the material itself. So it's actually more or less a measure to qualify the ongoing corrosion. The same applies with the Nyquist plots over Harrison solution. As you can see, the capacitive loops are decreasing over time, but here you can see that there is a more gradual degradation. But I will try to make them clear with tensile test results. These are the results after EXCO time. As you can see, after 6 hours or 24 or 48 hours, the material itself lost almost half of its ductility. So this is very critical for aircraft structures, because aircraft structures should be damage tolerant and should maintain their elongation at fracture. Or okay, I have to appropriately. You cannot see the slides. The images are of low quality, but in case I will try to imagine, you have some pitting, exfoliation, extremely exfoliation after 48 hours. How the story goes with sodium chloride? Sodium chloride is a more milder solution, showing that you have a gradual degradation in the tensile mechanical performance. As you can see, up to 420 hours, you can see actually no reduction. And after 168 hours, you can see actually no pores, no pitting. But after 2160 hours, when you have increased degradation, then you can, my apologies, you cannot see it. Here there are some localized corrosion very close to the fracture. Here is supposed to be the fracture of the specimen. And finally, these are the results for the Harrison's results, showing that gradually, after there is a gradual degradation of the elongation at fracture with increasing exposure to the solution. Here you can see what is the difference. The difference with the solution, with the Harrison solution, is you have more localized corrosion. And this was the initiation point in most of the specimens that fractured. So this is something that we will try to investigate in the near future and figure out the initiation of localized corrosion and what is the effect with fracture. So summing up, this is my small presentation. I will sum up with the elongation at fracture for all these three different solutions, starting from the EXCO. Here you can see the scale is upper bar. So you can see this is a gradual degradation of elongation at fracture, showing with areas of no pitting, some nucleation of pittings, and of course we have extreme deterioration after 48 hours, I will suppose after 24 hours. But how the story goes with the Harrison ones, so there is, for the Harrison one, you can see there is an inclination and linear degradation of elongation at fracture for the small exposure hours, up to 720 hours. And then you have extreme deterioration due to localized corrosion. And finally, for the sodium chloride, it's something different with the Harrison ones, showing that the nucleation of pits is rather prolonged, and nevertheless the degrees of degradation is similar to the Harrison ones. So this means that the corrosion degradation rate, as far as elongation at fracture is concerned, is more or less the same. So, and this is something that we will try to investigate in the near future. And our goal is to have something like a guidelines showing, for example, the extrapolation of or comparison between the different solutions, saying, for example, 5 hours of exfoliation corrosion is equivalent to 270 exfoliation time to hours to sodium chloride, something kind like of a benchmarking between the two solutions. So I don't want to stay on the conclusions. You had an idea with regard to our preliminary work. It's a 6 months time work, and I would like to thank you all for your attention.